Hey, hey. The Holocene has ended. What we do now and in the next few years will profoundly affect the next few thousand years. The only conditions modern humans have ever known so far are changing, and changing fast.
Nothing stays the same on this planet. Everything changes. The Earth is going into one of these jumps, and you don't know what is going to be on the other side of those jumps. The Earth is always jumping. Things move on this planet. Things are not still. Everything is turning.
As it begins to run out of fuel, the sun won't simply fade away to nothing. Its core will collapse, and the extra heat this generates will cause its outer layers to expand. The sun is now dead. It remains slowly cooling in the freezing temperatures of deep space. The fate of the sun is the same as for all stars. One day they must all eventually die, and the cosmos will be plunged into eternal night.
All stars eventually will run out of fuel. The temperature of the universe drops. The stars, one by one, in the night sky, will turn off. And there'll be no more new stars created. And so that the universe will end not with a bang, but with a whimper. And not in fire, but in ice.
With no fuel left to burn, a white dwarf's faint glow comes from the last residual heat from its extinguished furnace. Looking at it from where the Earth is now, it would only generate the same amount of light as the full moon on a clear night. The faint glow of white dwarfs will provide the only illumination in a dark and empty void littered with dead stars and black holes.
In some ways, it's kind of a ghost universe. It's the corpses, the zombie stars, that will take us into the future.
A black dwarf will be the final fate of those last stars. White dwarfs that have become so cold that they barely emit any more heat or light. Black dwarfs are dark, dense, decaying balls of degenerate matter, little more than the ashes of stars. Their constituent atoms are so severely crushed that black dwarfs are 1,000,000 times denser than our sun. Stars take so long to reach this point, we believe there are currently no black dwarfs in the universe.
We have a pace of life that's based on really the energy available to us now. You could imagine living conscious systems which have a very different pace and therefore can extend out at least a lot farther than you'd imagine otherwise. You could have a living system where if it had a thought every 10 trillion years, that would seem normal. Even if our life dies out, one could imagine at some time arbitrarily far in the future, a fluctuation occurs which allows intelligent life to exist again for a little while. So you might have islands in time of intelligence.
A proton, one of the fundamental building blocks of atomic matter, what makes us up, can just spontaneously fall apart.
Any material that evades the pull of a black hole eventually dies away as its protons disintegrate.
The matter inside black dwarfs, the last matter in the universe, will eventually evaporate away and be carried off into the void as radiation, leaving absolutely nothing behind. With the black dwarfs gone, there won't be a single atom of matter left. All that will remain of our once rich cosmos will be particles of light and black holes. The arrow of time creates a bright window in the universe's adolescence, during which life is possible. But it's a window that doesn't stay open for long. As a fraction of the lifespan of the universe, as measured from its beginning to the evaporation of the last black hole, life, as we know it, is only possible for 1,000th of a billion billionth of a percent.
Black holes become the fundamental building block of the universe. A galaxy will basically be a supermassive black hole in a center with smaller black holes orbiting it.
Zombie galaxies filled with black holes continue to evolve.
They'll eat each other and they'll get bigger, and maybe they'll fall into the supermassive black hole and it'll get bigger. The universe will still be an exciting, dynamic place. It's just that the timescales you're talking about are now trillions of years instead of thousands or millions of years.
Black holes can bang on space-time like mallets on a drum. And they have a very characteristic song. Imagine two black holes that have lived a long life together. At the end of their lives, they're going around each other, crossing thousands of kilometers in a fraction of a second. As they do so, they leave behind in their wake a ringing of space, an actual wave on space-time. Space squeezes and stretches as it emanates out from these black holes banging on the universe. Those are the gravitational waves. They are literally the sounds of space ringing. And they will travel out from these black holes at the speed of light as they ring down and coalesce to one spinning, quiet black hole. If you were standing near enough, your ear would resonate with the squeezing and stretching of space. You would literally hear the sound. Imagine a lighter black hole falling into a very heavy black hole. The sound you're hearing is a light black hole banging on space each time it gets close. As it falls in, it gets faster and it gets louder.
Scientists used to think black holes were immortal, but even these will one day die.
Now we're talking about timescales of unimaginable length, quadrillions of years into the future. On that timescale, even the black holes begin to evaporate.
According to quantum mechanics, space is filled with virtual particles and antiparticles that are constantly materializing in pairs, separating, coming together again, and annihilating each other. In the presence of a black hole, one member of a pair of virtual particles may fall into the hole, leaving the other member without a partner with which to annihilate. The forsaken particle appears to be radiation emitted by the black hole. And so, black holes are not eternal. They evaporate away at an increasing rate until they vanish in a gigantic explosion. Quantum mechanics has allowed particles and radiation to escape from the ultimate prison, a black hole.
Philosophers and poets have asked the question, will the world end in fire or ice? We can now give an answer. The latest evidence shows that the universe is not slowing down, but it's speeding up out of control. And the universe, we think, will die in ice. Trillions upon trillions of years from now.
Empty space itself has energy. In every little cubic centimeter of space, whether or not there's stuff whether or not there's particles, matter, radiation, or whatever, there is still energy, even in the space itself. And this energy, according to Einstein, exerts a push on the universe.
What is the weird stuff that's accelerating the universe? We call it dark energy. And this stuff is the dominant stuff of the universe. Almost 3/4 of the matter-energy content of the universe is this dark energy. And we don't know what it is.
Dark energy, unlike matter or radiation, does not dilute away as the universe expands. This has crucial implications for what the universe is going to do in the future.
So what will be the future of the universe? Well, if the dark energy remains dominant and repulsive, the universe will expand forever. Faster and faster and faster with time. A runaway universe.
70% of the energy of the universe resides in empty space, and we don't understand why. But we do know what will happen. If that energy continues to be there, the universe will become cold and dark and empty. That's the future as it might be. We don't know because we don't yet understand the nature of dark energy. Until we do, we won't know the future. We won't even understand our own origins. And that's why we want to know and study this subject.
Forecast does seem to be for an ever colder, ever emptier universe. But then, of course, we have to ask, could that end lead to a new beginning? And there are ideas whereby what actually is the end of our universe could in some sense be linked to the beginning of a new one.
We've worked out the mathematics, the equations. They seem to say that if you have an atom smasher that can concentrate tremendous amounts of energy at a single point, you can perhaps open up a gateway, a baby universe. Facing the death of everything there is, this perhaps is their only possibility of escape. And this also raises a very intriguing possibility, sheer speculation of course, that perhaps any universe that has intelligent life in it will create baby universes, will create lifeboats, and proliferate child universes. So an evolution may take among universes in the multiverse. Survival of the fittest may take place. So those universes which do not have intelligent life are infertile. They have no children. But those universes that have mild temperatures, stars like us, would create civilizations that could open up child universes, and they would then proliferate.
After an unimaginable length of time, even the black holes will have evaporated, and the universe will be nothing but a sea of photons gradually tending towards the same temperature as the expansion of the universe cools them towards absolute zero. Once the very last remnants of the very last stars have finally decayed away to nothing, and everything reaches the same temperature, the story of the universe finally comes to an end. For the first time in its life, the universe will be permanent and unchanging. Entropy finally stops increasing because the cosmos cannot get any more disordered. Nothing happens, and it keeps not happening forever.
It's Monday. It's 1 o'clock rock. We have Heather Kaluna here. She is a postdoc fellow at HIGP, the Hawaii Institute of Geophysics and Planetology. and she is into space weather, and that is exactly why we're calling this show Space Has Weather Too. Hi, Heather.
Hey, how's it going?
It's good, now that you're here. So, buses us with weather in space. I mean, are you kidding?
No, I'm not kidding. I mean, weather on Earth, for the most part, is stuff that erodes surfaces, right? So if you leave something outside, even if it's just a pair of slippers, over time it starts to get dried, eroded, a little bit like gray, right? The colors change. And so the same thing happens in space, but there's different processes that are responsible for it. So for example, I'm interested primarily in micrometeorite impacts. So there's
Would
basically
you say that again?
micrometeorite impacts.
I haven't heard of that. We do not discuss that at my dinner table.
Oh, wonderful.
Qu'est-ce que c'est que ça?
It's basically little dust particles flying through space
Okay.
that impact different surfaces.
Okay.
And space weathering really is important only for those bodies that don't have an atmosphere. Basically, they don't have something to protect them from these particles. And so when you look at the night sky and you see a little shooting star, that's basically a little speck of dust entering our atmosphere.
Ah.
And so if I was on an asteroid, for example, I didn't have an atmosphere, that speck of dust would come straight through and hit me. And so what
And
that
it hurt you.
It would hurt me,
Yeah.
just a little bit.
Yeah.
Of course, these objects get bigger in size, and we see,
It would hurt more.
it would hurt a lot more. But fortunately, those occur much less frequently. So, yeah, so space weathering, primarily what I study is these micrometeorite impacts. But there are other sources of space weathering, such as the solar wind. And so, are you familiar with the solar wind at all?
No.
So, it might be a bit of a surprise. Kind of like the wind we have here on Earth, it's a flow of particles that are moving past you. The solar wind is a flow of particles that come out from the sun. And so these happen to be charged particles like hydrogen and helium. And so these particles, as they fly through space, can also impact surfaces that don't have atmospheres. And they also erode the surfaces over time.
Like sandpaper.
Kind of like sandpaper.
Dig a little hole.
Very fine
Very
sandpaper.
fine sandpaper.
Yeah.
Like sandblasting.
Like sandblasting.
Slower, though.
Yeah, exactly.
Oh, how interesting. So, you call it weather. That's a pretty loose connection, isn't it? I mean, what does weather mean in the space context? It means solar wind. It means micrometeorite impact. What else?
Well, those are the two major components for the most part. I mean, but you also have, solar radiation. So you have sunlight hitting your surface.
Three then.
Yeah, you have stuff baking basically in the sun.
Yeah. So these things, it's not constant. Not the solar wind, not the micrometer impact, and not the solar radiation. They change.
Well, the solar wind and the solar radiation is pretty constant, right? So we're constantly receiving sunlight from the sun. It only gets dark on Earth because our portion of the Earth rotates out of view of the sun. But the sun is still shining, and so the solar wind is operating the same way like the radiation. It's constantly flowing out of the sun. You might have some bursts due to some activity on the sun. You might have an eruption on the surface of the sun that sends out basically a large surplus of these particles. And so in that sense, you can get a flux or a variation in this, these particles. The micrometeorites, now, you're right, that does change. That isn't constant.
What changes the rate of micro impact?
The impacts depend on where your object is. So if you look at the moon, for example, you have impacts, occurring every 10 seconds, every few minutes.
Okay.
But as you get to different parts of the solar system, so say you get further out towards Jupiter, you're going to have a different density of dust. There's not going to be necessarily as many particles, and so you won't have as many, your frequency of these impacts is going to be less.
So your job, should you decide to accept, as a space weather person, researcher person, scientist person, is to find out what causes these changes. Am I right? Or where you can find these phenomena, and what makes them happen here, not there, or happen this way, not that way. Tell me what it is.
Yeah, basically. as my astronomy background takes me into observing asteroid surfaces. And so what I want to see is actually how these processes affect the surfaces over time. And so I look at young asteroids and I look at old asteroids and I see how do they change? How does the spectra of these asteroids change?
So you're looking at the surface to see how they were beat up by these various phenomena.
Mm-hmm. And how it manifests in the colors or the spectra of the asteroid. And so are you familiar with a spectrum?
No, I assume I'm a carte blanche.
Okay. A rainbow is essentially a spectrum. So when you take white light and you shine it through a prism and it produces a rainbow, that rainbow is your spectrum, except instead of recording on a telescope computer, it's recording on your eye, right? You see those colors and they're recording on your eye. But what you're doing is you're taking that white light and you're splitting it into a bunch of different colors. So you're splitting it into its individual components. And so what I do is I study these colors of these asteroids. And over time, what we see is that certain colors actually get affected more prominently than others as a result of space weathering. And what happens is, unfortunately, this is where space weathering, there's a downside to it in the sense of we use spectra, so we use these colors to try to understand the compositions of asteroids, right? We can't send spacecraft there anytime we want. It's an expensive endeavor. Very rarely have we been able to sample these asteroids.
Yeah, they move fast and they have orbits that you don't know where they're going, I guess.
Yeah, it gets pretty complicated.
Yeah.
And then it's even more so complicated to, say, land a spacecraft on an asteroid, collect a sample, and bring it back.
Oh, that would be hard.
That would be hard.
And you
Fortunately,
would regret probably having tried.
there is one, the Japanese actually have done this for an asteroid that was nearby Earth.
A human person?
Not a human person. It was a
nice
robotic.
Machine.
Yeah. No people necessary. But it successfully landed on the surface. Some dust on the surface got knocked into a little carrier that got delivered back to Earth. And so that's the only asteroid we've ever directly sampled.
So if you got the dust from whatever the container was that the Japanese picked up off the asteroid, what would you do with the dust? What would you look for? How would you look at it?
Right. So there's people who actually specialize in this, and this is a little outside of my field. But what I do is, aside from my observations of asteroids in the lab, I simulate these processes by using a laser, a pulsar laser, that basically heats up and vaporizes whatever sample I put in, my lab.
Could be a rock. It is a rock.
It's usually a ground-up rock.
Okay.
So to simulate the dust that you see on the surfaces of the asteroids. But what I'm trying to simulate is exactly what we find in these samples that the Japanese picked up. So we see these little melt blobs, right? They're basically regions where the little micrometeorite came in and hit the surface. The heat from that impact vaporized some material, and some of that material cools down and recondenses on the grain surrounding it.
How can you tell the difference between the material that was vaporized and fell back down again and the material that was there in the first place?
So you can actually, just looking at, there's really amazing instrumentation nowadays that can get you really down to a very fine scale. Basically, you can see, things on the scale of the thickness of your hair.
Okay.
And so you get down to this detail and you actually start to see things pop out. And it literally looks like a giant melt blob, like you piled a big glob of glue on a melt grain. And it's like, okay, that's not a normal mineral
So you
structure.
compare it against what you see in the background.
Exactly.
And it looks different, like a blob maybe.
Yeah.
And then you start looking at that. So now you have your blob.
Right.
What do you do with the blob?
So I should actually take a step back.
Okay.
We know about space weathering actually from the Apollo missions.
Oh, really?
And so the astronauts brought back samples from the moon.
Okay.
And these samples included rocks and soils, right? So some of this this lunar dust. And when you look at the lunar dust, you can actually see these same things, these melt blobs. You can also see, if you cut one of these lunar soil grains in half, you actually see that there's a glassy rim around some of these grains. And within that glassy rim, there's nanometer-sized metallic iron particles. And so this is not always, but for the most part, we see it pretty pervasively in the samples.
Okay.
And so it's interesting because people wondered, all right, what is this that we're seeing? What's causing it? And part of what I'm investigating is whether or not, it's the solar wind that isn't primarily responsible for producing these features, or is these micrometeorite impacts? And so there's a big question about which one is the more dominant process. However, what's interesting is that if you look at these soils, right, that were collected directly from the moon, and if you compare it to a soil that you make by grinding up a lunar rock.
Sorry, I don't know the answer.
Oh, that's so interesting. That's her echo machine. You must have said something that triggered her. But clearly she didn't know the answer.
She doesn't know the answer. That's really interesting. I did that to my phone recently too. I don't know. Maybe
That's
it's
so
my
funny.
voice.
This is time for a break. We're going to take a short break, and we're going to turn her off.
Okay.
Okay, that's Heather Kaluna. She's a postdoc fellow at HIGP at UH Manoa, and she's researching space weathering at HIGP. This is Research at Manoa, Space Weathering. Space has weathering too. We'll be right back.
Hi, I'm Ethan Allen, host of Likeable Science on ThinkTech Hawaii. I hope you'll join me each Friday afternoon as we explore the amazing world of science. We bring on interesting guests, scientists from all walks of life, from all walks of science, to talk about the work they do, why they do it, and moreover, why it's interesting to you. What the science really means to your life, its impacts on you, how it's shaping the world around you, and why you should care about it. I do hope you'll join me every Friday at 2 p.m. for Likeable Science.
Looking to energize your Friday afternoon? Tune in to Stan the Energy Man at 12 noon. Aloha Friday here on ThinkTech Hawaii.
Aloha, my name is Mark Shklov. I am the host of Law Across the Sea. Please join me every other Monday to hear lawyers from Hawaii discussing ways to reach across the sea and help people and bring people together. Aloha.
Okay, we're back on Research in Manoa, 1 o'clock block on every Monday. And we have Heather Kaluna. She's a postdoc fellow at HIGP, the Hawaii Institute of Geophysics and Planetology, and talking to us about her research, which is space weathering. So, Heather, how did you get into this business? Did you wake up one morning and say, I like to study space weathering?
Well, really, it's an interesting question. I got into this business through my PhD program. And so,
Which was?
Astronomy. So I went to the Institute for Astronomy, which is our master's and PhD program at the University of Hawaii at Manoa. And when I first went there, my advisor, she's actually someone who we call an astrobiologist. Have you heard of an astrobiologist?
I have, but I never did understand it, though.
It's basically an interdisciplinary sort of perspective on astronomy and life in the universe.
Mm-hmm.
And what she did when I was trying to find an advisor, she spoke to me about this topic that it just hit me, and it was so amazing. And the topic is the origin of Earth's water. And you might be thinking, how is this related to space weather?
I am thinking that.
And I will get there. But what's really interesting is that we think that Earth formed so close to the sun that it actually was too warm for it to have its own water, and that water had to be delivered through impacts from comets and surprisingly wet asteroids. And so I got really interested in these wet asteroids.
Because it was a mystery.
It's a mystery. And I'm born and raised on Big Island. I'm a water girl all the way. Grew up by the beach. And so, really being able to study water in space was really fascinating to me. However, in order to characterize which asteroids have water on them, getting back to these spectral features or these colors and these fingerprints, if space weathering is removing and making some of these fingerprints disappear, that reduces our ability to detect these water-rich asteroids or characterize their water composition.
It's like the traces of what happened before washed away, like in the beach, the sand and the waves wash away the history of it.
You slowly start to see the words disappear every time the wave comes up, right?
Yeah.
And so that's why I got into space weathering. It's like, I'm really interested in this question of, how much water did asteroids contribute to Earth's, our oceans? And so, in order to answer that, we first have to look at this question of space weathering. How does space weathering modify these features that we use to characterize the water and the water history?
Can I roll it back for a minute, though? Why do you say water? Water is so easy to make. All you need is hydrogen and oxygen.
Mm-hmm.
Why wasn't there hydrogen and oxygen here on Earth? And why wasn't there some sort of natural process, some kind of physical phenomenon that happened that put them together as water? Why does it have to be external delivery?
Right. And so that has to do with the temperature, basically, right? So when you look at the inner planets, they're primarily rocky bodies, right? But as soon as you get out to, the inner planets are like Mars, Mercury, Earth, Venus.
Mm-hmm.
But as soon as you get out to Jupiter, the game changes, right? You have suddenly a huge, massive planet that has actually a ton of hydrogen in it. And this has to do with the fact that there was a certain temperature in our solar system when it was forming. So when our planets were forming, there's a certain temperature away from where the star is forming, our sun is forming, basically in the center, where the temperatures get cool enough that water in the vapor, basically in the gas, we call it the solar nebula, but water exists as a gas form close into the sun. And once you get to a certain distance, that vapor can actually turn into a solid and can turn into water ice. And so as little
Vapor is steam. We're talking about steam, right?
Basically, yeah.
Okay.
And so this vapor, once it becomes solid, can now become incorporated into these, we call them protoplanets. They're like little planetary embryos of a sort, or eggs. And so that's where it becomes important, is because if you're too close to the star, if you're too close to the sun, you're only going to have solid materials that are hitting each other and sticking to each other, right? You're not going to have gases that just suddenly collide and clump together. Like, we don't see that,
Well, why? Why don't? Because the sun will burn them off, or the gravity of the sun will pull them in. Why are they not there?
So the water is there in vapor form near Earth, but you can kind of think of it as like, if you're outside and you're throwing around a bunch of pieces of mud, are you going to have the water and the air stick to the mud? Not necessarily, right?
Mm-hmm.
It's the mud that's going to be sticking to each other for the most part.
Yes, I see.
And so that's essentially what's going on. I mean, that's the best analogy I can come up.
It's a medium.
It's a medium, right?
Yeah.
And so basically the inner planets only formed from the stuff that was solid. And most of the planets in the outer solar system, like Jupiter, Saturn, and whatnot, because they were able to form from a combination of ice and rocks, right? They got their cores built up very quickly. Their gravity became so massive that they actually could steal some of the gas, the hydrogen gas that was around them. So that's why they have these giant gaseous envelopes. But Earth and the other planets in the inner solar system never got big enough to be able to trap gases quite like that.
So have you been developing a theory about how all the water actually got here, the delivery of the water? I mean, I can imagine these planets that are largely water somehow, and what they come down from heaven and splat. They're on Earth. I mean, I've splat's the wrong sound.
No, splat's great. I like splat. Because that means it's a nice wet asteroid.
Do you have a theory about how this happened?
So this is actually a little beyond what I do. And that's where, we have these big picture questions in science, right? So this is the end game. This is the gold medal. One day, hopefully, once we piece together all the little components that everyone's working on, we can actually answer that question. So I'm personally not trying to figure out, how these asteroids got here. There's people who design models and try to, see if Jupiter and Saturn moved in our solar system as it was forming, how does that toss things around? And they look at that kind of thing.
Oh.
But instead, I'm looking at these spectral features of these asteroids to see, given this knowledge of what we see today, can we trace back to what these objects were like when they first formed? So that way we can actually see, these impacts that hit the Earth early when it was forming. How much water did they give us?
Okay, so what's happening today because you can.
Well, I'm trying to figure out what's happening today.
Well, aside from the Japanese dust,
Mm-hmm.
how else can you do spectral analysis of what's going on the asteroid? I mean, you can look at it through a telescope.
Yeah. So I go up to Mauna Kea. I've spent quite a few nights up there sitting at the telescope, and I tell you, it makes you quite loopy up there, I swear.
Oh, sure. When you get to it, I've been at Mauna Loa,
Mm-hmm.
and I know how that works.
Yeah,
It's a really
there's
weird
a very
feeling.
subtle difference in elevation there. I use the telescopes. We have special instruments that take the light coming in from an asteroid and make a spectrum out of it. So we have basically a prism inside the telescope that splits the light up, and we can start to search for those fingerprints that tell us that there's water-rich minerals on these asteroids, or there's water itself on the asteroid.
Okay, so now you know the composition, which is complicated, of an asteroid. You know about the globs and everything on the asteroid, and you know, so you're learning the real time characteristics of the asteroid and the existence of the water on the asteroid. But how can you compare that against the way it was a long time ago? You can't see that anymore. How do you know the way it was a long time ago?
So this is where models come into play. And so that's why the observations are very important. Because in order to really, I mean, you can model anything, honestly, and say, hey, this is how it was. But if you don't have the observations to really give it some ground truth, you're not going to be able to say much. And so that's why these observations are important. Because if I can say, you know, these many asteroids have water on them, then they can start to say, okay, well, based on our model of the early solar system and the temperatures and, you know, the amount of bodies that were in that region, they can say, this is how many objects we expected to impact the Earth based on our model. And so it really comes down to taking the observations and tying it into the models.
So you're working it backward.
Working it backwards. That's all we can do is work it backwards.
Yeah, because I mean, we're talking about, what, millions of years ago?
Millions, billions of years ago.
Oh, sorry.
Yeah, I mean, yeah.
Okay, so this is pretty sophisticated stuff. What kind of instrument? I mean, if I go with you one morning to your laboratory in HIGP, and I walk in, what am I going to see there? Can you describe it for me?
Yeah. So you basically have this long rectangular tube that actually houses a laser. And so it's an infrared laser, and we can't actually see that with our eyes.
Okay.
And so if I was to turn it on, you wouldn't actually be able to see it like fire out of the tube.
It wouldn't hurt me though.
It would hurt you.
Oh, sorry.
It could zap you. So like if we put a little piece of paper in front of our laser, it will zap.
Okay.
And so, you know, I don't think it'd burn a hole through your hand unless you just leave it there. And so, yes, so you have this laser. It goes through, there's a couple lenses to help redirect the laser down onto our sample. Our sample itself actually sits in this chamber. It's this giant metal round. It's almost like a ball.
Okay, but it's only this big.
Yeah, it's not very big. I mean, our samples, we literally, you know, I use a 0.5 gram of powder in our samples. But we put it inside this chamber, and we shut the chamber, and we actually pump the air out of it. So we try to get it down to pressures that are close to what we see in space. So very low vacuum type pressures.
You're just trying to emulate the pressure in space. You're not getting it down to zero.
Exactly.
Zero. Okay.
Yeah. And so, so we put our sample inside the chamber, close it, get the air out of there, and we turn on the laser, and it's pulsed, so it's meant to sort of speed up the impact process, right? So the impacts don't occur, you know, instantaneously and continuously like you're asking. But we also don't have time to sit here and simulate it exactly according to the rate that happens in space.
Yeah.
So we speed up the process by pulsing the laser, right? Yeah. And so we do, you know, once every 20 pulses a second is how quickly we're actually bombarding our sample.
Okay.
And so we do that for whatever period of time we're interested in doing it for.
Until lunch.
Usually I'll do like a few minutes.
Okay.
Take it out of the chamber, and then I have a spectrometer. And so this is a thing that images, you know, it takes the light, splits it up, and it images my sample. So I can actually see how these features vary.
So you can see the elements from the periodic table, what's what, right? Isn't that what this spectroscopy does?
Yeah, but instead of elements, we're actually looking at minerals. So there's specific features that correspond to minerals like olivine and pyroxene. My favorite minerals, the ones that I'm interested in, are these clay minerals. So they're basically muddy clay minerals.
Because there's water in there.
Yeah, because there's water in there. And we call them phyllosilicates. And really, honestly, as a graduate student coming from an astronomy background, this was a whole new ballgame.
Sure, yeah.
And honestly,
there's some pictures. We had a picture a minute ago.
Really?
Okay.
Oh, okay.
So, all right. So, I just want to get, we have a couple of minutes left.
Okay.
I just want to get where this fits. You spoke before. There are some scientific leaders out there who have been thinking about the comprehensive and where all this fits, what you're doing and others, and sort of the look back on how it was way back when, and how and sort of to find lessons about how the universe works and how the weather works and those three kinds of weather phenomena that you have.
I mean, they become important
Yeah.
for asteroids. I mean, when you talk about space travel,
Yeah.
these processes are important. Understanding how do they affect people, much less, asteroids, is an important thing to quantify.
I mean, if you're on an asteroid, or if you're on a planet, if you're on Mars,
if
for
you're on the moon, these kind of things are
so it
definite.
could be bad. You could have a solar storm and it would really give you a headache.
Exactly.
So what about identifying asteroids coming in? That's not part of it, though?
That's not what I do, but there are people who do that.
Yeah.
And so, but that's what
Okay, so I'm Joe Blow, walking down the street.
Okay.
How does your research affect me? And that's a hard one, I know. How does your research affect me? How are you thinking of me, and how should I be thinking of you in terms of the connection of science and our daily lives?
I think there's two answers I could give to that. The first one comes back to this origin of water. That's really water is essential for life. And so it's kind of getting back to our origin story from a scientific perspective. And I think that, is important to anyone. I think religion is a big thing because people care about their origins. And so I think that's why what I do is really important, at least to me.
Yeah.
And the other answer is, aside from our origins, it's also our future.
Yeah.
And so if we look at space travel and space flight, there's a whole new group of people trying to, SpaceX, all these groups that are trying to develop technologies to have more space travel. And one of the possibilities that we can do is actually, this is a idea that is floating around out there, and I think it's exciting.
Floating is the operative word, yeah.
But the idea is to use asteroids with water on them that have these clay minerals to refuel. So say, you're flying through space and you only had so much fuel to get you to, say, the moon. But there's an asteroid nearby that has water features on it, and you can say, hey, look at this asteroid. I know there's water on it. I can stop by there, have my little contraption, whatever that's for someone else to design.
Get the water out of it.
Get the water out of it, refuel my spacecraft, and then mosey on to wherever I want to go next.
But that raises, maybe it's inherent in that question, but it raises, in my mind, another question. That is, we're having problems with water already on this planet. And in the years to come, we'll probably have more profound problems with it. And maybe, just maybe, we'll find out more about water and the origin of water. We'll find out how it got here in the first place. Maybe we'll find out how to get more of it. Is that part of what you're doing?
I've never thought about it like that, but that is an interesting perspective. Hopefully we never have to get to that point.
Okay.
But one of the things that does, one of the questions that does pop up in this research topic is, is the water on the surface of the Earth all the water there is, right? So we have oceans and there's, a seafloor. But what about the water? Is there water trapped in our mantle? Is there water trapped in the magma, the lava that is beneath the surface of our Earth? And people think there is. And some people think there might be 5 times our ocean's worth of water submerged in the magma.
And we can learn about that from looking at space.
Yeah.
We can learn about water, which is an essential part of life.
Yeah, it all fits into that story. It's another piece of the puzzle.
Yeah, another piece of the puzzle. Well, thank you for working on the puzzle for us, Heather.
Thank you for appreciating it.
Come back and talk more about your studies and your research and your writing. This is Heather Kaluna. She's a PhD in astronomy at IFA, and she's a postdoc fellow at HIGP studying space weathering. What an interesting discussion. Thank you, Heather.
I hope you enjoyed.
Thank you very much.
Awesome.
Aloha.
Aloha.